So think about this for a second. If a chip company is just completely blocked from getting, the world's absolute most advanced lithography machines, are they just doomed to lag behind forever?
Well, that's the trillion-dollar question, right? I mean, the traditional logic says, yes, they're stuck, but engineering is weird.
Yeah.
Sometimes a massive roadblock just forces you to, well, invent a totally new road.
Right. Which brings us to today's deep dive. We are looking at a really massive report from Bloomberg this week about a huge, high-stakes gamble in the semiconductor world.
Yeah, it's a big one.
Basically, Huawei has proposed this radically new chip architecture to try and bypass their lack of advanced equipment. And the ultimate goal, to shorten the gap with TSMC.
And our mission today is really to separate the actual reality from all the crazy hype we're seeing.
Because there is a lot of hype right now.
Exactly.
Mm-hmm.
We're going to look at exactly what Bloomberg reported, try to decipher these really complex new engineering concepts Huawei is throwing around, and, figure out what an equivalent 1.4 nanometer chip actually means for the global chip war.
So let's start by just throwing a bucket of cold water on some of these headlines. Because I've seen takes online implying that Huawei is already secretly mass-producing 1.4 nanometer chips right now.
Oh, yeah. No. We need to be super clear on this. That is definitely not what is happening. Not even close.
Right. So Bloomberg reported on a presentation by Huawei's head of semiconductors, He Tingbo. And she didn't announce a product launch. It was a roadmap, like a goal to manufacture 1.4 nanometer chips by 2031.
Yeah, 2031, that's a target node, a theoretical pathway.
It's like announcing you've invented a revolutionary new running shoe and you plan to break the marathon record in 5 years.
Right.
Like, it's a cool plan, but you haven't actually run the race yet.
That's a great way to put it. And it's really crucial for you, the listener, to understand what 1.4 nanometer even means here. We aren't like taking a tiny ruler and measuring physical gates on a transistor anymore.
Right, it's not a literal measurement.
Exactly. A target node like 1.4 nanometer is basically shorthand for a performance benchmark. It means you have a specific density of transistors, a certain speed, and a certain power efficiency.
Okay, so she outlined a strategy to reach that benchmark by 2031.
Yeah.
But having a strategy on paper is very different from actually having millions of chips rolling off a factory line today.
Totally. Which naturally leads to the question of, well, why do they even need this distant radical roadmap in the first place?
Right. Why not just do what everyone else is doing?
Because the traditional path has a giant, basically immovable roadblock sitting right in the middle of it.
And that roadblock is EUV lithography, extreme ultraviolet.
Right. EUV is the absolute non-negotiable tool you need for mass-producing chips at 5 nanometers and below using normal methods.
And just to clarify, the Dutch company ASML is the critical gatekeeper here, right? Like, because of U.S. export controls, Chinese companies just cannot buy these advanced EUV machines.
Yeah, they are completely locked out of the most advanced versions.
Let's unpack that a bit. Imagine EUV is like this microscopic, ultra-fine-tipped pen. If you want to draw the intricate blueprints of a modern chip, you absolutely need this pen. The export controls essentially, well, they hid all the fine-tipped pens.
I like that analogy. And you might wonder, why not just build your own fine-tipped pen?
Well, because EUV isn't just a normal upgrade. It's pushing the absolute edge of physics.
How so? Like, what makes it so crazy hard to build?
So to get this specific wavelength of extreme ultraviolet light, the machine fires a high-power industrial laser at microscopic droplets of molten tin.
Wait, molten tin?
Yeah, molten tin falling through a vacuum chamber, and the laser blasts these tiny droplets 50,000 times a second.
Oh, wow. That's insane.
Right. It vaporizes the tin into a plasma that emits the light. But the light is so delicate that it gets absorbed by literally anything, even air.
So you can't even use normal glass lenses? Nope. You have to bounce this light through a series of flawlessly smooth mirrors in a total vacuum just to focus it onto the silicon wafer. It's widely considered to be the most complex machine humans have ever built.
So if you can't buy that machine, you're stuck with the older generation of machines, DUV or deep ultraviolet.
Exactly. And trying to draw a 1.4 nanometer circuit with DUV is like trying to draw fine details with a giant thick marker. You have to use multi-patterning. You draw one part, etch it, put down a new stencil, draw the next part, and so on.
And every single time, it has to align perfectly.
Down to the nanometer. If there's even a tiny vibration, the circuit shorts out and the chip is totally useless.
So this brings up a really interesting question for you guys listening. If you're a company whose access to this advanced equipment is just totally cut off, what do you think is the better move? Do you stubbornly try to recreate that exact same EUV equipment from scratch, or do you abandon that path and look for an entirely alternative architecture?
Well, according to the Bloomberg report, Huawei is proposing the alternative path. If they can't get the fine-tipped pen to shrink the physical transistors efficiently, they are moving away from the traditional Moore's Law approach.
Right, and this is where it gets really interesting. They propose two new concepts, the Tau scaling law and the logic folding architecture. And Huawei actually stated their future Kirin mobile chips are going to be the first to adopt this logic folding thing.
Yeah, when you first hear those terms, they sound like sci-fi jargon, but there's real physics behind them.
So let me try an analogy here. Think of the old method, Moore's Law, like trying to make all the furniture in a room smaller so you can cram more of it in.
Okay, yeah.
Huawei's logic folding and Tau scaling law are saying, what if we stop shrinking the furniture and instead completely redesign the room's layout?
Yeah.
Like, what if we fold the space so data can travel faster, reducing resistance and making the whole thing more efficient?
That is actually a really good way to visualize it, because Tau scaling law focuses on time, not just physical space. Specifically, it targets time constants, or RC delay.
RC delay, that's resistance and capacitance, right?
Exactly. As you cram more tiny transistors together, the wires connecting them get thinner, which spikes the resistance. And because they're so close, the capacitance goes up.
So it's like you built a super fast Ferrari, but you're forcing it to drive on a gridlocked one-lane dirt road.
Right. The Ferrari is useless if the road is terrible. So Tau scaling law says, let's optimize the road network so the signal gets from point A to point B faster. And logic folding is the physical way they plan to do that.
But how do you actually fold a logic circuit? Like, physically?
Think about standard chip design, like a flat 2D city plan. If data needs to go from a processor to memory on the other side of the chip, it has to travel across a long, flat wire. Long wire equals high resistance.
Okay, so folding implies moving to 3D, building skyscrapers to bring things closer together.
Basically, yes. It's a radical restructuring of the 3D space, lowering the resistance and capacitance loads, which boosts your data transfer speeds structurally.
So you get the performance of a 1.4 nanometer chip, but you're actually using larger, easier to manufacture transistors.
That's the theory. You change the layout to bypass the need for the absolute smallest physical shrinkage.
Okay, so Huawei has this clever new room layout idea, but we have to look at the actual calendar here, because Bloomberg specifically focused on the gap between this plan and TSMC.
Right. TSMC is universally viewed as the undisputed benchmark for advanced manufacturing right now.
And Bloomberg noted there's currently roughly a 5-year gap between TSMC's capabilities and those of Huawei and its manufacturing partner, SM.
5 years is a massive amount of time in semiconductors. It's the difference between, running a cutting-edge AI data center and playing games on an old smartphone.
So let's look at the dates. Bloomberg noted TSMC plans to mass produce 1.4 nanometer chips by 2028, but Huawei is targeting 2031 for their logic folding version. That's a huge detail.
It really is, because it proves two things at once. First, it shows that China's advanced manufacturing has not caught up yet. The sanctions, factually, created a severe bottleneck. But second, it puts a real ticking clock on the race. If Huawei's alternative route actually works, it could genuinely compress a gap that those export controls were basically designed to maintain permanently.
Okay, but if this is just a roadmap for 2031 and TSMC is still years ahead, why did the financial world react like they just crossed the finish line?
Oh, the market reaction was wild. After the Bloomberg report dropped, Chinese semiconductor stocks surged. The Shanghai Star 50 index jumped, SMIC stock went up over 18% at one point, and Huahong Semiconductor hit its 20% upper limit.
Wait a second. If this tech is still years away from actually being put in a phone, why is the stock market throwing a massive party right now? It doesn't make sense.
Well, you got to remember, the market is pricing in expectation, not a technological reality. For a long time, investors assumed that without EUV, Chinese chip makers were facing a literal dead end.
Right, just a brick wall.
Exactly. So this surge reflects massive investor relief that a credible potential bypass even exists. But, and this is a big but, capital enthusiasm doesn't magically solve physics problems.
Yeah, throwing money at a stock ticker doesn't fix a broken silicon wafer. Which brings us to the really grueling part of this deep dive, the actual test.
Right, getting from a whiteboard to a smartphone.
Exactly. So I want to ask you, the listener, directly. Think about this transition. What do you think is the single biggest pitfall between having a brilliant technological breakthrough on paper and actually achieving commercial mass production.
Because it's not just about making one brilliant chip in a lab. It's about yield rates, cost control, and stability.
If you're using older DUV machines with insane multi-patterning to print these new folded structures, your chance of defects goes through the roof.
Right. And if only 10% of your chips actually work, your cost per chip is astronomical. You can't sell a phone that costs $50,000 to make.
But even if they solve the manufacturing yield, there's another massive hurdle, right?
Oh, yeah. The software ecosystem, especially for AI chips. Because AI computing isn't just about one fast chip. It requires massive clusters, memory, and a software stack that actually knows how to use the hardware.
Right, like NVIDIA's CUDA platform. Millions of developers know how to use it.
Exactly. If Huawei introduces a totally new physical layout with logic folding, the EDA tools the software used to design the chips have to be completely rewritten.
So even if the logic folding hardware works perfectly, if the global developers and compilers don't adapt to it, it just won't succeed commercially.
It's basically like trying to invent a new type of car engine, but you also have to invent the new fuel, rewrite the repair manuals, and convince every mechanic on Earth to learn your new system, all while under a massive embargo.
By 2031, it is a monumental task.
It really is.
So to wrap this all up, the Bloomberg report is definitely not a victory declaration for anyone.
No, absolutely not.
It's evidence of a strategic pivot in the global chip war. They're moving from simply chasing the exact same advanced manufacturing nodes to trying to invent alternative architectures under very strict constraints.
And that pivot is going to define the industry for the next decade.
Which leaves us with a final, pretty provocative thought for you to ponder. When you look at the next 10 years of this technological race, what do you think will be the absolute most critical factor?
Is it going to be the domestic development of EUV machines? Advanced packaging, entirely new AI chip architectures like logic folding? Or at the end of the day, is it all going to come down to the software ecosystem?
It is a massive question, and we would absolutely love to hear your thoughts on it. Thanks for hanging out with us for this deep dive, and we'll catch you next time.